Alright, so this is E658 lecture 43. So far in our discussions we have seen one, how to get at a physically realizable NTF. From the NTF you can get the loop filter transfer function, right? And from the loop filter transfer function you can actually go and implement the loop filter itself. Okay, so we have seen for example in the second order case we found the loop filter, and we saw, as we expected, that the loop filter should have at low frequencies it must go as 1 by 1 minus the inverse the whole square, because at low frequencies the gain must go as, the gain of the loop filter at low frequencies must go as pardon? The loop filter gain, not the NTF gain. The NTF gain must go as omega square, so the loop filter gain must go as 1 over omega square. Alright, and in general, if you have an nth order modulator with all zeros at the omega equal to 0 or z equal to 1, we found that you should have at least n integrators in the loop filter, and there will be of course feed forward branches which add the outputs of various integrators and realize the loop filter output. So the next thing that I want to discuss is the mechanics of actually before I go there, another thing that we discussed is one way of finding the maximum stable amplitude. And how would we do this? So the basic idea is to take the loop filter, which is something like this. This is the quantizer. This is a slow ramp, okay, which goes from 0 to Vref by 2. The range of the quantizer is denoted by minus Vref by 2 to plus Vref by 2. So this is a slow ramp which goes all the way from 0 to Vref by 2 in a large number of steps. Typically I like to use 1,000,000, right? And somewhere along the line, I mean clearly we know that when the input hits Vref by 2, the quantizer is saturated and the guy is going unstable. But before that happens, you will find that if you plot the magnitude of the quantizer input on the log scale, you will find that this is y, so log of mod y. If I plot, you will find that it will do this and then suddenly just take off like this. The value of the input at this point, okay, gives you the maximum stable amplitude, right? Okay, and this method kind of works quite nicely for multi-bit quantizers, right? So by multi-bit quantization, what I mean is that there are many levels in this quantizer, and not surprisingly, people said if you can do better and better noise shaping, then you can get the same output signal to noise ratio by using fewer and fewer levels in the quantizer, right? So what is the absolute limit? What is the lowest number of levels you can use in the quantizer? You obviously can't get into the quantizer itself, right? So you need at least 2 levels. So use a 1-bit quantizer. Okay. So traditionally the 1-bit quantizers were the first to come, simply because of the ease of implementation of a single bit quantizer. It's just one comparator and you're done with it, right? So a lot of early work in delta sigma modulation is all based on single bit quantizers. multi-bit quantizers were thought to be difficult to do and difficult to implement, and were also associated with few other problems. I will come to that when I get there. But but over the last few years, people have realized that multi-bit operation offers a lot of advantages over single bit modulation. One thing, of course, which we can understand still at this level is the fact that as the number of levels become larger and larger and larger, the approximation of the quantizer being a linear system, right, with this additive noise, that model becomes better and better. And you've seen this from your from your simulations on quantizers and so on. You've seen that that's the trend you saw. So and it and fundamentally it also makes sense, because see, if you had only a 1-bit quantizer, your basic quantizer is doing such a sloppy job, and you have to clean up after the quantizer by doing a lot of noise shaping, right? So presumably if your basic quantizer is doing a reasonable job, you'll be doing much better. That's all that there is to it. So we figured that out. So let me just illustrate this thing and in MATLAB, and one thing that I want you guys to do is to download this Schreier's, I keep forgetting spelling, Schreier Delta Sigma Toolbox. I think it's hosted in several places, one of them being the MATLAB site. Okay, so this is a bunch of very, very useful utilities to do Delta Sigma design. And so this is an example of, let me just see if, okay, I don't know if you're able to read the print or what at the back. So this is MATLAB script. So as you can see, I have specified the order to be 3, the oversampling ratio to be 64, the order band gain to be 3, the number of levels in the quantizer is 15, the sampling rate is the oversampling ratio times twice the signal bandwidth. This is intended for audio, so the signal bandwidth is up to 24 kilohertz. So twice 24 kilohertz times the oversampling ratio gives the sampling rate of the converter. There's this nice command that this all uses commands from the toolbox. Okay, so I just say synthesize noise transfer function order OSR order band gain, and it actually gives you the noise transfer function itself. Okay, and you can see that when I plot the magnitude of the noise transfer function, the gain is the outer band gain is indeed 3. Okay, and there's nothing great I have done here. It's all part of the code, so you can do the same thing too. All right. So it just takes maybe a little playing around to get used to the toolbox. But once you get used to it, life is very simple. Then I decide to find the maximum stable amplitude of the modulator, right? And what do? I generate a ramp which goes from 0 to the number of levels, right? The way he implements the quantizer is that the LSB size is always fixed at 2, and if there are more levels, the range of the quantizer goes on increasing. Correct? That's the way he's implemented. So the quantizer range goes from minus n level to plus n level with increments of 2. All right. That's not what you would do in a real circuit, because in a real circuit the top and bottom rails are fixed. If you want more levels, the LSB size goes on reducing. To implement it in code, apparently this is easier to do, which is why he probably chose this way. So I run the input as a slow ramp from 0 starts from 0 and goes to the topmost rail over a million samples, and there is this nice routine which given the input, the noise transfer function, the number of levels in the quantizer, will basically simulate will write the difference, generate the difference equations and actually simulate the entire modulator. Okay, it even has what do you call a provision for setting random initial conditions within the loop filter is a dynamic network, right? It's got memory. So presumably the output of the loop filter depends on the initial conditions you set. Okay, so there is basically a provision to do that, and what I have done is simply assign those initial conditions to some random numbers. Okay, which is what would happen in practice. So if I plot, and the convention that we have adopted in the course is very similar to what he does in the toolbox. So Y1 stands for the Y stands for the input to the quantizer, and V stands for the quantizer output. And as you can probably see, if I plot say log 10 absolute value of V, what is this now? So what I need is log 10 of absolute value of Y, which is so you can see that in the beginning the input to the quantizer originally is hovering around between, the input is 0 originally, right? So it's hovering around between around 2 and 0 and minus 2 and so on. So the log of that quantity is negative. As you go on increasing the input, you can see that the log also gently increases, which is what you would expect with a log. But the moment the input reaches about somewhere around 90,000 points, right? So on the x-axis is the number of points. Recall that we were going from 0 to Vref in a million points. That's 10 power 6. Okay. So the moment that reaches around 90,000 or so, you can see that the log has jumped up by about 10 to 12 orders of magnitude. Okay, which basically means that the state variable is just blown up. Okay, the outputs have just gone to infinity. So the maximum stable amplitude here, as you can read off from this graph, is simply about 90% of full scale. All right. So now that we have figured out that the maximum stable amplitude is that much, the next thing to do is to run simulations with a sine wave. Why you want to find the maximum stable amplitude in the first place is to figure out what is the maximum amplitude you can push into the modulator, right? So you can't clearly push in full scale, because when the sine wave goes beyond this maximum stable amplitude, the modulator will go unstable. And to be a little safe, I've just I've defined the maximum stable amplitude as not the point at which the input to the quantizer just goes to infinity, but a 10% margin. I've taken 0.9 times that. And so the next thing is basically I generate a sine wave whose amplitude is the same as the maximum stable amplitude, right? And okay, and you can see, and this is the output for a sine wave. Okay, so you can see that the output takes on only discrete levels. Okay, and if you kind of zoom in a little bit, you'll see most of the time that the output kind of seems well behaved, and the jumps, you can see, for instance, that the output jumps by 2 LSB a lot more often than we saw in the second order case. I don't know if you remember, but with the first order case, we saw that the output was always jumping up and down by just 1 LSB, correct? when we went to the second order case, during the transition we found that occasionally some of those guys would jump up by 2 LSB. Okay. Here we see that this 2 LSB seems to be a regular feature, right? You can see that the jumps, especially around here, right? This seems to be jumping up and about by 2 LSB with almost all the time. Okay. What else do we observe from this graph? You also observe that the LSB is 2, so it just jumps up from 8 to 10 and 10 to 12 and so on. Does that make sense? Okay. So since yes, there are 15 levels, so it's minus minus 1. The switching points are even. Let me see. 15, the n level is 15. No, if there are even, that's not correct. So the 0 is a threshold, and so are 2, 4, 6, and so on. So yes, the levels should be odd. That is no, the levels should be even also. No. Yes, actually there must be, the outputs must have, there must be 15 levels. So 0 must be a level, not a switching threshold. The switching threshold must be plus minus 1. If there are 15 levels at the output, 0 must be a level, and then there must be 7 levels on top and 7 levels below. If you want, if the quantizer output must have 15 levels, and if you want to make it a symmetric characteristic, then 0 must be a level, and there must be 7 levels on top and 7 levels below, right? I think it's straightforward. This is a 15 level quantizer, yes. No, you can have any number of levels you want, right? This just happens to be 15 levels, that's all. It turns out that
in the worst case, say if we have a 1-bit quantizer.
Correct, the outputs.
Is it minus 1 or plus 1?
Correct.
The threshold is 0.
Yes.
So extrapolating minus 1 plus 1.
No, that's because there are 2 levels in the quantizer. Right? So if you have 3 levels, the output will be, the levels will be 0, plus 2 and minus 2. That's all. Okay. So, okay. The next thing, pardon?
150
What is this?
Isn't y greater than 1?
Yeah, I just find when y takes off beyond 150, it could be 200.
We should be bothered about it. It should not go beyond the rail.
No. See, the moment the modulator becomes unstable, it will go up by 10 orders of magnitude in 2 time steps. So whether it goes up beyond 150 or whether it goes up beyond 1,50,000 doesn't make any difference. Pardon? Correct. No, you find the index at which this is all MATLAB script. It's like you find if you want me to explain it to you, is you find the index beyond which y goes up, beyond 150, right? And then find the u corresponding to that. That's all. All right, and what will happen if you use find is that there will be several indexes beyond which the output goes to, because it keeps toggling, right? So there could be several indexes, so you find the minimum, and this is all like.
Yeah, it's given by Xmax only.
Pardon?
Why don't we just use Xmax there, because command will directly give Xmax the max and
it will give you the correct within the entire, no, it will give you Xmax with oh, by the way, before I run away, this Xmax here, the toolbox will give you the output V, the input to the quantizer Y, and Xn stands for the state variables. Okay, for all the state variables inside the filter. If you have an nth order filter, there will be n state variables. It will give you, all those state variables. It assumes some standard way in which the loop filter is built, and it also gives you Xmax, which happens to be the maximum values that these state variables take on during the entire simulation cycle. Okay, the reason why you need the state variables and their maximum will become apparent a little later on when we get into the implementation details. But at this point, all that you care about is V and Y. Okay, you need Y to estimate the maximum stable amplitude, and you need the output, obviously. Does this make sense? Okay. The next thing is to put in a sine wave and actually simulate the modulator, and as I showed you, the output will be a quantized sine wave, and you want to be able to figure out how clean the, you want to figure out what the spectrum is within the signal band. So what you do is to use this, is to find the path spectral density of the sequence. The path spectral density, okay, okay, so you can see that this is pardon? No, PSD, because the record length is very large, the PSD by definition will average out FFTs of with durations of it will average out many records. Okay, so let me get into the, before I get into the details of this, couple of things are come to mind. So you have this output sine wave. Okay, so what do you think? So if I wanted you to find the signal to noise ratio within the signal band, what would you do based on the knowledge you have accumulated in this course so far? What would you do?
Put it on the within the band.
No, okay, forget about this. So I gave you the output waveform of the delta sigma, right? So it's got this jagged, it's basically a sine wave with some shaped quantization noise. What do you want to do next? You want to figure out if your delta sigma is working properly or not. So what you want to do is to actually measure the in band signal to quantization noise ratio, just like how we did for a Nyquist converter. Is the only difference between an oversampled converter and a Nyquist converter is that in the Nyquist converter, the signal to quantization noise ratio is measured in the following way. You find the signal power, right? And everything other than the signal bin is quantization noise. Okay, so you take this ratio of this power to that power, and then you do dB and all this other stuff and get whatever number you get. In an oversampled converter, the band of interest is only pi by OSR. Okay, which basically, and why is it so if I do an FFT of the, in principle if I just do compute the FFT of the modulator output, okay, it will have components all the way from 0 to pi radians per sec, pi radians, or 0 to fs by 2, correct, equivalently. But I am not interested in all the entire spectrum. Why? Yes, because in practice what happens is that I am not going to be using this sigma delta output as is. I am going to go through a sharp digital low pass filter, which in principle will reject everything outside pi by OSR. Okay, so the portion of the spectrum I am interested in is only this low frequency part, which is 0 to pi by OSR. Okay, and I can multiply that by the appropriate scaling number to get instead of going on talking in terms of submultiples of pi, I can relabel the x-axis so that it corresponds from 0 to the analog bandwidth. Okay, so fs by 2 will correspond to in our case the oversampling ratio is 64, the signal bandwidth is 24 kilohertz, so the sampling rate happens to be about 3 megahertz. Okay, and the signal band is 24 kilohertz, so I will the band of interest therefore is to look from 0 to 24 kilohertz. Is that clear? Okay, so based on your experience so far, you would think that I will put the signal in what do you call in one of the on the bin, correct? That's what from our experience with Nyquist converters, this is what we have done. We have taken the input signal sine wave, put it on one of the bins, okay, and you run FFT with a rectangular window, and everything is hunky dory, you're all fine. Okay. So, do you think, what do you think will happen if I did the same thing with a delta sigma modulator output? Is there any fundamental difference between the output of a delta sigma and the output of a Nyquist state converter? So, as I said, the next thing is estimating in band signal to quantization noise ratio. All right. So, you have this black box sigma delta modulator. The V is what is coming out, the U is what is going in. All right, and the V is a discrete time signal whose sampling rate is Fs. So, you are interested in the spectrum. You are generally expecting to see a spectrum like this with the signal being like this. All right, and the bandwidth of interest is 0 to pi by OSR, and this goes all the way from 0 to. Does make sense? Okay. All right. So, so can you think of any difference between the output of a Nyquist state converter and a delta sigma? I mean, the approximation you have for the delta sigma is that it is some loop filter and some uniformly distributed quantization noise. All right. So, can you tell me some difference that you can think of between these two?
More uniformity in the quantization noise.
Pardon?
There's more uniformity in the quantization noise in the Nyquist converter.
What do you mean by uniformity?
The noise is not shaped at all.
Yes, okay. Yes. I mean, we do that where? I mean, in a Nyquist converter, I mean, what we have learned is the following: we should sync the input source with the clock, right? And then you choose this magic ratio of numbers, which makes sure that you're not hitting the same points all over again, right? And the tone must lie on a bin, and the usual stuff, and you run the FFT, and lo and behold, you'll see one single spike corresponding to the input. The rest of it is quantization noise. You're done. Okay, right? So, in other words, as long as the input tone is synchronized with the clock in a Nyquist converter, you do not need to use a window to FFT. A rectangular window is good enough, because with the rectangular window, what are we doing? When we sample the spectrum, you are sampling the sink at integral multiples of 1 over t, right? So basically you will be sampling all the zeros, and you just get you don't see the Eiffel Tower. Okay. Now, so is there any difference between that and this situation? To lead you to the answer, let me see what happens if EFN was 0. Let me take a sample data system like this. Okay, you have some discrete time loop filter. I deliberately choose E of n to be 0. I can always simulate a system like this. I can take any loop filter, put 0 there, and then feed it back and look at the output. Correct? So if this was a sine wave, in steady state, what will the output V be? it will be another sinusoid, okay. So if that sinusoid is again related to the sampling rate by a rational number, right, I can use a rectangular window and I should get only one single spike and the rest of it must be 0 because there's all the other coefficients must be 0 because there's nothing else, there's no quantization, it's a linear system, right. If I put in a pure tone at the input, I must get a pure tone at the output, okay. So clearly with no quantization noise, there is no need to use a window, correct, okay. Now if this was uniform random noise, as we have assumed, yes. Wait, yeah, I'll come to that before that, okay. So our model for this delta sigma is that the quantizer is acting like a additive noise source, where the noise is uniformly distributed and is uncorrelated with the input and all this wonderful stuff. So now can you comment on the situation? The output V consists of two components because this is a linear system. The first component is the input signal itself, and because of the way I have chosen the input, I told you that we can choose it such that it lies on a bin. So in other words, the input can be chosen such that this sequence is a periodic sequence, okay. Is that clear? Alright. Now unfortunately along with the input you have the shape quantization noise, okay, which is you have to just assume that it's a sequence, okay, and actually this doesn't look like shape quantization noise at all. Actually it's very difficult to draw a random noise waveform. So hopefully this is more uncorrelated than the earlier one, okay. You understand? So if it's if this E of n is a random uncorrelated noise, random noise uncorrelated from sample to sample, what can you say about the noise sequence coming out of the modulator? It is this random sequence which is shaped by a loop by a transfer function equal to the NTF, which is 1 by 1 plus L of Z, okay. But is that output periodic or it's not periodic? It is not periodic, okay. So if I sample this sequence, I am only taking a finite record, okay. Blah blah blah, okay. So now if I compute the coefficients of the discrete Fourier series for the combined sequence V, which has got a periodic sequence corresponding to the input plus an aperiodic sequence corresponding to the noise, what can happen? If I just use a rectangular window, what can happen? No, there is no Eiffel Tower to begin with. If I mean it's noise. Yes.
So when we even though we
pardon? There will be.
When you repeat the sequence, then there will be a huge peak at the end.
Okay. Intuitively, what is happening is the following. So what I mean is when you take a rectangular window, when you take a chunk of data and compute its DFS coefficients, what you are doing is assuming the following, that the sequence is periodic, okay, and you are finding the Fourier series coefficients of this periodic extension of the record, okay. So now if for the signal part there is no problem at all, you will see a single spike because the signal is nice and periodic, right. The record, if I copy and paste an adjacent record after this record, there will be no jump at all between two records because the signal happens to be periodic. But noise by its very nature is not periodic at all, correct? So what happens? There will be a discontinuity at, so whatever, right? So the noise here and the noise here will not be the same. So in other words, it's like finding the Fourier series of a nice sine wave plus some waveform where there are discontinuities at, there are jumps in the waveform at, in the beginning and the end, correct? If there is a jump in the waveform of in a sequence, what is that equivalent to? A jump in a sequence is nothing but an impulse, correct? And what is the spectral density of the impulse? It will be flat, okay? So what you will see, okay, in practice is if there are discontinuities in the noise waveform at the beginning and end of the cycle, what you will see is that it's like adding an impulse, so it will flatten out the, actually the noise the component of the noise spectral density at DC must be 0, correct? At very low frequencies it must go up as omega cube in this case, alright? Not omega cube, omega to the power 6. If it's a third order modulator, the spectral density is shaped by NTF whole square, so it must go as omega to the power 6. So at low values of the frequency, you are expecting the noise spectral density to go to 0. Is that clear? Okay. But now because of thanks to the way you are computing the Fourier series, there are discontinuities at the edges of the data record, which is equivalent to adding impulses, which will cause this thing to, you will not see the thing actually plummeting to 0, you will see something which is flat. You understand? So when you do that, what will happen is you will see something like this and then something which kind of flattens off and it will not go to 0. Does it make sense? And depending on the data record, alright, this flat part is clearly a function of the difference in the first and last, parts of the waveform, correct? So, depending on the record you take, for some records you might find that you are lucky and you get, a very low, this flat portion being very, very small, okay. Some other case you might find that this flat portion is very, very large. Does it make sense? Okay. So, so what do? You have to de-emphasize the edges. You want only the center. So, just as we've discussed this at great length in earlier classes, right? So, all that you need to do is take the data sequence and apply a window. Alright. So, a popular window used is for simulation. So, the Han window, okay. So the Han window is nothing but a raised cosine window, which looks like this. So you can see that the gain of the parts towards the end is 0 in comparison to the stuff at the middle. Alright. And what did we see with regard to the Han window earlier on? It will spread this, so while the Han window definitely, reduces the problem due to discontinuity of this quantization noise waveform, it also smudges the input signal, the input sinusoid across 3 bins rather than 1 bin. Okay. So, this is how it looks, okay, and rectangular window. Any case hand width direct is it? I hope. So let's see. I never. Yeah, I know. So the question is, let's see what happens if you use a rectangular window itself. And by Murphy's law, it will come out perfectly well the first time I do it. Is that the Welch? Okay, let's try that. I think the default is hand. I think the default is hand. Yeah. I think the default is also hand, if I am not mistaken. But the record length is different. So no, because the record length is not. It takes the entire record and makes a F50. I think that's the problem. Actually, let me do that offline and show it to you tomorrow. So let me just plot the F50 of. How many? 1, 2, 3, 4, 5. For 23, I doubt it. Yeah, you can see the plot is great. Okay, so if you do, all that I have taken is 1024 points of the output of the modulator and just run F50 as we were wont to doing when we were dealing with a Nyquist converter. And what you see is that okay, so here if you kind of observe the trend, you can see that the what do you call the shape noise is reducing, okay, but beyond a certain point it just simply becomes flat because the shape noise is supposed to have gone down like this, okay, but then there is discontinuity and that just gets that just fills up all the lower pins. You follow? So that is the problem with using a rectangular window to in delta sigma modulator measurements. Oh God, no. Okay. the next thing that I want to cover is the fact that, as you can see, this okay. So hand windowing is a very nice thing to do, especially in simulation. And the hand window will result in a spectrum which generally will look like this, okay, and this will be sitting over it will be sitting over this shaped spectrum like this, okay. And let us say this is pi by OSR. So to find the signal power, what should you do? You add these three bins. No, you don't add the logs up. You add the squares of the FFT coefficients. Okay. So this all right. And to find the noise power, what do you do? You add up the powers in all these bins, okay. And you know, it's see, a lot of more any practical delta sigma modulator will have DC offset, so you can neglect the very first bin and the second bin, because if you take DC offset and pass it through a hand window, it will spread to the first bin as well as the second bin, okay. So you can remove a couple of bins in the beginning, and but add up the powers in the rest of the bins, of course not removing the signal bin. I mean, you should remove the signal bin to get the noise power, okay. And so 10 log to the base 10 signal power and noise power should give you the signal to quantization. Please note that this is only quantization noise, signal to quantization noise ratio in dB. You understand? So to come to his point, the point he made was that, see, all this is very nice, provided the quantization noise is truly random, okay, and white. But clearly we know that the quantization noise, I mean, the whole system is deterministic, there is nothing random about it at all, okay, because given the input I can actually find the exact output by solving the loop and so on. So fortunately it turns out, if you have you know, a reasonably high order, so say third order and higher, and you have multi-bit operation, that is the number of levels in the quantizer are large, okay, this noise, the so called quantization noise, largely appears random, okay, alright. But if you have single bit quantizers and low order modulation, right, so let's say you try and do a second order modulator with a single bit quantizer, you will actually find that when you do I mean, you can definitely find input sequences which will cause the output sequence to become periodic, okay. I will not go into the details here. I have set up an assignment to illustrate this point. By the way, the fifth assignment, is it? Fifth is due day after tomorrow, okay. So how many of you guys have actually started attempted it at all? Oh, okay, so that's not too bad. So okay. So how long did it take? Those who attempted, how long has it, how many problems have you finished and how long has it taken? Not finished anything?
First and second have
First problem, it's all MATLAB and right fit only, no? I mean, okay, my assessment would be the first wouldn't take more than about an hour or so. Is that reasonable estimate? So, so which basically means that one problem 1 hour means 3 problems, you know, around. The second one probably will take a little longer for you guys because you're not used to the simulation yet, but. And now I don't remember the third problem at all. Some DAC. The third one is going to likely take a little more time. So anyway, so if you, I mean, I'm sure this will only lead to trouble, but let me just say this anyway. So if you want to do this, I mean, if the majority of the class agrees, I can, you know, I can push the deadline to 10th, but there's an additional assignment. So, you know, you can submit both assignments by 10th. Okay. So, I mean, so now on 9th you'll have like, you know, 10 problems to do rather than.
Can you push the 6th assignment to the 7th deadline?
And 7th at.
Sir, we have 7th, we have assignment, 8th we have exam, 9th I have exam, and 10th we have.
Okay, so I'll push the 6th. No, see this. Okay, the reason, okay, so let me do the following, right? So the 5th assignment, I'll push the deadline to 21st, okay, which is, you know, 10 more days than you said. But I do want the 6th assignment to be done as soon as possible. Okay, by 10th, I do want the 6th assignment. The idea in having the assignment is to, you know, for you guys to actually do these things and then figure these out yourself. Otherwise, I mean, in class everything looks alright, okay, only the moment you start doing things you find that nothing works and you have trouble, alright. And this stuff is actually quite fun, you know, it's all MATLAB, so there is no, you know, beating around VDS and VGS and all this, you know, complicated stuff, right. And, I mean, generating random numbers is all pretty nice, interesting stuff, especially when you don't do anything, right. And, there's toolbox, you know, you should get familiar with it anyway. So this is a nice, the 6th assignment doesn't even, you know, require you to do the toolbox, it just, you know, wants you to write some difference equations and see for yourself, you know, amazingly how these things work. So the 6th, I do want the assignment submitted on 10th. I think the 6th will not take too much time. Okay. The 7th requires, you know, you to be able to follow this delta sigma modulator theory and then as well as this area of implementing the loop filter itself through using continuous time circuits. That's what I will cover in the next, you know, several classes. But without knowing how to fool around with the toolbox, you know, you will not be able to do the 7th assignment. The 7th assignment is also in fact, almost all of it is MATLAB based, except that I ask you to verify it using ideal op amps and resistors and capacitors in a simulator. But 6th is something that I definitely want you to submit on 10th. And please don't do it on 9th, you know, it's like, the idea is for you to learn, okay, it's not for you to beat the system and, you know, whatever, right. No, I don't think there's first of all, I don't, okay, so there are some of these N2 guys whom you want to kill later, okay, so who want to do transistor level, you know, that's what I had in mind in the beginning of the class, right, because you did your 4-bit flash, so you can put it to the DAC and then, you know, at least close the loop around a real, more real looking modulator but I don't think there's enough time for that. So if you have so much time, maybe you should practice your cricketing skills a little better. Okay, so what else? Yeah, so before I just wind up in a couple of minutes. So as you can see, the this quantization noise kind of appears random, all right, even though technically it isn't. Okay, it's very much deterministic, but it appears random, and that randomness kind of increases as the number of levels in the quantizer increase and the order increases. Okay. Now, so assuming now that the model of additive quantization noise is valid, then depending on the record and depending on the particular noise realization, you are likely to end up with different values of signal to quantization noise ratio. You understand? Because the input signal is fixed and clean, but this uniform random noise that is being added Okay, it depends on, sometimes it's noise, after all it's stochastic. So the if you take a small record, for some records the power might be small, for other records the power might be large. Okay, so to get rid of to get rid of estimation errors of signal to quantization noise ratio because of randomness of the noise waveform, what you will do is to simulate it over many record lengths. Okay, for each record length you estimate the SNR. In other words, you find the FFT coefficients for each record length and then average out the powers in every bin. Do you understand? So you simulate for many record lengths, right? So 1, 2, whatever, right? So this is N record, this is also N record, and so on. So you find the FFT of this sequence windowed by the hand window, alright. You find the FFT of this sequence windowed by the hand window and this windowed by the hand window, alright. And simply in every bin other than the signal bins, the magnitude of the power will keep changing, because the noise waveform during this record length is different from the noise here, which is different from the noise here. You would think that the noise power would be approximately constant, but there will be some variation simply because the noise waveform is random. Does it make sense? Okay. So what to average this out, what you do is you take the FFT. You take the FFTs and simply average their powers. Okay. So this is intuitively what happens in what is called this PSD, this sparse spectral density estimation program that you have in MATLAB. It divides up, chops up the input into many records. Okay, with the record lengths you can specify. For each of these records, it computes the windowed FFT, right? Finds the powers in each bin, and then averages it across the entire data length, right? So the record length is not to be confused with the data length. So this is the total length of simulation. This, on the other hand, is the FFT record length. Okay. So all it is doing is chopping up this total simulation data into many records, right? Computing windowed FFTs on each of them, finding the power in each bin, averaging the powers across the entire data simulation length. Does it make sense? Yeah. So before I get there, the one question is, as you average different FFTs, what do you think will happen to the what do you call? See, if you did the FFT of only one record length, you will see the nice signal spectrum that you're always used to seeing, correct? But since noise is a random phenomena, for one thing, so for one realization, you probably get something like this, okay? For another realization record length, you probably get something like this. For third one, you get something like this, okay? So when you average many record lengths, FFTs, what would you expect?
You get closer to the tube.
You should get
Smoother wave.
a smoother waveform, okay? You understand? So which is why if you look at this spectrum, sorry, this, of course there is a problem with windowing because we are not windowed it, that's the flat part of the spectrum there, right? But if you look at the fuzz on the waveform on the computed spectrum, there is only one record, okay? So you can see that there is a lot of jumping up and down, correct? Whereas if I had plotted okay, anyway, the earlier spectrum with the hand windowed PSD was nice and smooth, right? and that's because I have averaged, the record length is the same, but the simulation length is very long, so there are many record lengths within the whole simulation interval. So I've got so many, I've averaged many FFTs, which makes the thing look nice and smooth. You understand? So I'm sorry for keeping you late today. I will stop.